All right, before we get started on this notes, we're going to be looking at some stuff from Math 1, the linear depreciation model and an exponential depreciation model. And so you are going to need a Desmos tab open, have it ready. Okay, so suppose you purchase a car for $27,000. According to online research, this make and model loses all of its marketable value after 12 years. That is, it depreciates to a value of $0 12 years after the purchase date. If the car depreciates in a straight line form, what are the coordinates of the intercepts? So remember, the intercepts are going to represent the starting value in year 0, how much it started at, and then they're going to represent the ending value after 12 years, how the value has gone to 0. So our coordinate is representing the number of years the car has been owned and the value of the vehicle. So to do the intercept for the first one, we were told that at year 0, it was worth $27,000. So that's our first intercept, our y-intercept, or our value intercept. And then the second one says that after 12 years, the value of it is 0. That would be our x-intercept, or the year's intercept. Now the problem just asks for the intercepts, but in class I did go through with everybody and say, well, what would be the slope of this? How much is it going down per year? So I reminded everybody of the equation m equals y2 minus y1 divided by x2 minus x1. And so we would go 0 minus 27,000 as your y minus y over 12 minus 0. And when you get negative 27,000 over 12, we get a slope of negative 2250. Let me see if I'm remembering that correct. Let's go do it in Desmos. So 27,000 divided by 12. Yep, negative 2250. Okay, good. So that's the slope. So what if I wanted to go write the equation for this? You could write with the first linear form, slope-intercept form. Slope-intercept form that you guys learned back in Math 1 is y equals mx plus b. So I start with my slope, negative 2250 per year, and my beginning value, my y-intercept, is 27,000. And this would be the equation of the line of it depreciating steadily 2250 per year. But the original question over here of the warm-up is linear depreciation a good model for a car's value? And what we're about to see in this lesson is it is not realistic to expect a car's value to go down a specific amount each year. It is more realistic that cars lose a lot of value at the beginning and then it slows down. Picture when you drive that car off the lot, it goes down a lot. So if a linear model is not the realistic model, well, which kind of a model is? So we're going to kind of go through this here together in this next reading. Okay. Not sure why there's that weird thing there. Okay. So let's go through the text together, and I'm going to highlight, and you can highlight with me. So how does a car lose its value? In the previous lesson, or I should have said warm-up, we examined automobile depreciation, where the car lost the same amount or dollar value each year. That's really not the case. You can often get a good idea of how a car loses value by looking at prices from the past. This information is known as the historical data. The devaluation of a car when using this type of data is called historical depreciation. There are many websites that list the prices of used cars. So we know this well-known website is called Kelley Blue Book. Before the internet, the Kelley Blue Book was an actual blue book of historical car prices that they published every year. Can you picture like looking through an actual book to get a car price? Now we just find everything on the internet. Look at this data for a Chevy Corvette in good condition. The table shows the age of the car in years and the value of the car. So the first year the car was owned, it was worth $24,000. After 6 years, it was worth this, and after 10 years, it's worth this. If I look at this model, notice how it drops more quickly at the beginning and then it starts to flatten out. The scatter plot of this data is shown. Notice it's not linear, but rather appears to be curved. The car value seems to have a greater drop at the beginning of the car's lifetime and less as the years pass. Notice that the depreciation is not constant. The depreciation is not constant from year to year. The scatter plot models an exponential decay function. Rather than the value decreasing by the same amount each year, it's decreasing by the same percentage. In the context of auto devaluation, this model is known as exponential depreciation. So, no, linear is not a good model. Exponential is a realistic model. So we're now going to explore using the exponential function that you guys learned in Math 1. The general form of this function is where A is the starting value of the car. So begins at what? What is that price that it begins with? I'm going to do that one in blue. And then R is the percentage of depreciation expressed as a decimal. I'm going to do that guy in green. And then X, the power of X, is your number of years. Let's do that one in pink. All right, so in this equation, A stands for the starting value of the car, R is for the percent depreciation, and X is the elapsed amount of time. All right, so here we have this new car for $23,000. It depreciates at a rate of 10% per year. Write the exponential function. So first of all, let's think about this 10% per year. 10% converted to a decimal would be 0.1. So I'm going to actually show you guys, go up here to insert equation, and it brings up this, and we're going to say y equals the A value, 23,000, times 1 minus the rate, converted rate is 0.1, to the power of 5 years. Now let me take a step back here, and I just want to insert the original equation where the 23,000 is the A value, 1 minus the rate, and to the power of X. And we are plugging in the A value of 23,000, the rate right there, and this time. So when I go put this into Desmos, I'm not going to put it, well, you technically could put it like that, but there's one step of simplification you guys would probably be okay with, like making that a 0.9. By the way, how am I getting this power here? Oops, I meant to copy and paste that one more time. I'm getting the power by doing the Shift 6 key. So right here, I go Shift 6, and it does that little up arrow hat thing, and then we can put the power of 5. There's also a function up here in the equation editor functions where there is a fraction, and there's also this x to the b. That's your exponent function if you need it. But I just use the Shift key. Okay, so we're going to go plug this into Desmos right now. 23,000 times 0.9 to the power of 5. And think about that. We're saying that it's 90% of the original value. That makes sense. And then every year, it's 90% of that, 90% of that, et cetera, et cetera. So I'm getting $13,581 and 27 cents. Hashtag, just kidding, that should be a $sign. And then there's my Desmos work in case we want to see the work. Okay, so thinking back to this equation in Math 1, if you're like, man, I didn't take this, or I don't remember this, or I have no idea what this equation is, great. It's just a new equation for you to plug into following these rules. So here's the rules, here's what it stands for. Okay, this next one is going to need Desmos graphing. So get that ready. And here we go. A car originally sold for $26,600 and it depreciates exponentially at a rate of 5.5 per year. When purchasing the car, this is how much he put down. So first, let's write the equation of the exponential decay or exponential depreciation model. So we're going to, again, use this function. Oops. Let's go copy and paste it from up there to save us some typing time. So they're telling us that it originally sold for $26,600 and it's depreciating at a rate of 5.5. So we're putting the starting value of $26,600 and the rate of 5.5 is going to be 0.055. Are you okay with how I got that? And it's to the power of x because after how many years? Well, we don't know. So that's what we're trying to figure out. We're trying to find out that value. So real quick, how did I get the 0.55? I'm taking 5.5 and I'm moving the decimal twice to the left. So I'm going 1, 2. And so that makes the decimal 0.055, moving it twice to the left. Is that okay? It's a very small percent. All right. Well, 1 minus 0.055, let's go figure out what that is in Desmos. And that's 0.945. All right, so this is our function, a times 0.945 to the power of x. This is the equation of exponential depreciation. Well, there's some other information in this problem. When purchasing the car, he put $6,000 down and he pays $400 per month to pay off the balance. After how many years will his car value equal the amount he paid? So we wrote the equation for the exponential decay, the car losing value. Now we're going to write the equation for how much he paid for the car. And this is going to be linear because he paid $6,000 outright and $400 per month. But that's the monthly, and we need annual. So we would say 6,000 down. And what would 400 a month times 12 months be? Exactly, 4,800 per year. So this is the annual figure we want to be able to compare. So now that we have both equations, they want us to graph them and see where they intersect. And that's where the car value is going to equal how much he's actually paid. All right, so we're going to go put 6,000 plus 48x, 4,800x, and 26,600 times 0.945 to the power of x. Let's go put those into Desmos and see how this looks. So y equals 26,600 times 0.945 to the power of x. I'm just going to use the shift key because it's hiding underneath there. And then my second one is y equals 6,000 plus 4,800 per year, or 4,800x. Now, when I look at my window over here, I'm like, what the heck? I can't see anything because we need to get up to 26,000. So clicking on this little wrench over here is going to help me adjust my window, my x and y axis. So I want to make this, I don't know, like 300 on the x-axis. Yay, now I can see the curve. And the y-axis, how high do I want to go? I want to go up to like 20,000. Let's try 30,000. Now we are talking. So do you see how we can now see the graph, this linear equation of how much he's putting into paying for the car and this exponential curve going down? Well, this is the key point right here of the point of intersection. So it's about 3.3 years, and the value is at about 22,000. Hang on, I want to go up a little bit. There it is. So if you need to see about what these worked out to, it's at about 228 on the x-axis, and it's about 27,000 on the y-axis, so that I could see this a little bit more clearly. And so I'm going to go ahead and show this dot so I can copy and paste it into the document. So 3.3, 22,000. All right. And so the car is worth the same as what I have put in at about 3.3 years. It's worth 22,000 or so. So where did I get that number again? Right here at this point of intersection, 3.3 and 22,022 is the value of the car. Okay, kind of cool to see. Takes about, a little bit over 3 years that how much I pay into the car is what it's actually worth. Interesting. Okay, a car exponentially depreciates at a rate of 6% per year, and a Kia purchased a 5-year-old car for $18,000. What is the original price of the car? This is an output problem. Instead of giving us the input, they're giving us the output, and we have to figure out. So real quick, I'm going to go back up here and copy and paste just to save myself some time on this equation. So what do we know from this problem? We know that it's worth 18,000 now. So we've been given the output, or the y. We don't know the value that it originally was. What was the original price of the car? A is what we're trying to find. And 6% depreciation in a 5-year-old car. So this X value up here is 5. And a 6% depreciation rate is 0.06 when we convert it. So I can do 1 minus 0.06. And do you guys see that that's going to be 0.94? And then we're going to divide both sides by the 0.94 to the power of 5. So insert equation. I want a fraction. So I'm going to get 18,000 divided by 0.94 to the power of 5. And this is what my A equals. So let's go plug that into Desmos and see what we get as the original price of the car. So 18,000 divided by 0.94 to the power of 5. And I'm getting an original car value of $24,526. $0.37. How'd you do? So you have to be able to use this equation both ways. You have to be given an input. Can you get the output? Given the output, can you get an input? So just be prepared to be able to go forwards and backwards on that. All right, example 6. Josh and Leah just bought this used car of $20,000. When this new car was sold, it was for $24,000. If the car depreciates, when the car was new, it was $24,000. So at year 0, and by the way, these are going to start to get too full. So let me just go ahead and delete some of these. Oh, that's super annoying now. Isn't there a way for me to make these all the same size? Just kidding. There we go. 1. Who knew? Okay, so I'm going to go ahead and center all this stuff and bold and red it. You guys know Miss Sanchez. Okay, so in year 0, in year 1, in year 2, in year 3, in year 4, the car's value was $24,000. And they bought a car at $20,000. So how old was it? So now we're just going to go down at that rate of 8%. So if I go grab a calculator, 1 minus 0.08, my multiplier is going to be a 0.92. So I'm going to go do the math here of 24,000 times 0.92. And there's my next value, 22,080. Now I'm going to take that number and repeatedly multiply it by the 0.92 until we hit 20,000. Okay, not quite 20,000, so let's do it one more time. 2313.6 times 0.92 is 18,688.51. So the car's value, or I should just say the car is between 2 and 3 years old when it hits 20,000. So where did I get that again? See how in year 2 it's 20,313, but in year 3 it's down to 18. So somewhere between 2 and 3 years old when it hits that $20,000 value. So again, we've been using the function, but here's another way of looking at it just straight up in a table. What did we multiply each section by? Times the 0.92 multiplier. Okay. According to an online company that supplies used car history reports, a certain make and model has the following value based on its age. The original price of the car is $24,000, so starting at the year 0, 24. If the pattern continues, what will it be worth when it's 7? So here's your here's your 0, your 1, 2, 3, 4, 5. We need to go 2 more consecutive times to see for year 7. So how are we going to do that? We need to figure out what the multiplier is. How do we do a multiplier? We need to divide. So we take the second term and divide it by the first term. So 21,600 divided by 24,000, and that gives us a multiplier of 0.9. Okay, let's see what the next term gives us. All right, the next term is 19,440 divided by 21,600. And oh, hey, look at that. It's the same multiplier, 0.9. What do you think is going to happen every time we divide all of these? You got it. It's going to keep coming out to 0.9. Let's do one more just to be safe. 496 divided by 19,440. And oh, look, it's 0.9. They're all going to come out to 0.9, just like you said. So now that I know my multiplier, I can continue the pattern. So we're going to take the 14,171.76 and multiply it by the 0.9 multiplier, and we get 12,754. And then we're going to do that one more time, 12,754 and 58 cents times 0.9. And there it is. After the year 7, its value is 11,479. When the car is 7 years old, it will be worth 11,479.13. There you go. How'd you do? Now, because that notes was so long, I made the practice super short. It's 2 questions. Woohoo! Good luck.